Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I am creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we're going to discuss about your cell structure and its hexagonal geometry. So these are the outlines. We're going to start up with the introduction where we're going to describe whatever we have studied in our last lecture. Then we're going to discuss about your cell structure, what should be its cell shape. Then we're going to discuss about your actual cell shape, how does it actually look like. Then we're going to discuss about the geometry of hexagon, that is what is so peculiar about the geometry of hexagon, so that it would have been considered as the standard of your cell shape. Then we're going to discuss how we're going to find the co-channel cells location. And finally, we're going to conclude by discussing one important ratio, that is our reuse ratio. What is it and how we have actually defined it. So in our last lecture, we have discussed about the basics of cellular concepts as well as anatomy of call, that is how a call will going to take place. Then we have also discussed about the need of frequency reusability. Now in this particular lecture, we are going to discuss about the shape of cell, that is what should be the shape of that cell and why the hexagonal structure would have been considered as the standard cell shape while cellular planning. So if this is the base station, then if we are considering this omnidirectional antenna, then its pattern will be just like this particular circular. So if we're going to consider this as your cellular structure and we basically try to make our cellular system, then we have to replicate this particular cell throughout the geographical coverage area like this. So here in this particular case, what we can observe it, if we are talking about these non-overlapping regions, there are certain void spaces here, as well as here. So there is large amount of void area is there where we do not have any sort of coverage. That is, it is the region where we do not have the coverage of any of the base station. So if a particular user will going to lie in this particular void space, then in this particular scenario, it will not going to get any sort of services from any of the base station. So that is why we can say that this sort of cellular structure is not good. Here one point I would like to mention over here is, please consider that if you are talking about your cellular planning, then cellular structure should be of 3D type. I mean the actual cell shape is a kind of sphere, but since we cannot show this 3D figure in this particular system, so that is why we are considering that your 2D structures. So pinpoint while considering this cellular structure of your cell structure is, we will going to have lots of void spaces where we will not going to have coverage of any base station. So that is why we should not use this particular shape for our cell structure. Then second two-dimensional structure where we're going to have those non-overlapping region is your triangle. That is, we can also have this triangular sort of cell shape. If we will going to standardize the cell shape as a triangle, then what types of problems we have to face is, in comparison to your circular cell shape, here this particular area, I mean in comparison to this circular shape, this triangular cell structure will going to have lower coverage area. So what we basically demand is, we should have to have install lower number of base stations and have the maximum amount of coverage. So this is all about our frequency planning so that we can minimize the cost also. So here in this particular case, if we are comparing our omnidirectional antenna like your cellular cell structure, so here in this particular case we have to install larger amount of base stations as the coverage of this triangular cell structure is very much lower in comparison to your cellular cell shape. So what else we could do is, so if we going to consider this square shape of cell structure, then what will going to happen is, again we will going to comparing this your circular cell shape. So at this particular moment also we will having these lesser amount of coverage area in comparison to your circular cell shape. Obviously in comparison to your triangular cell structure, this square cell structure coverage area is larger, but in comparison to this circular cell shape, it's quite lower. Next we may move on your pentagon and then your hexagon. So for a given radii r, a sphere has the maximum surface area. So we have also seen a pattern that as we will going to increase the size of your regular polygon, that is we are moving from triangular to square, then square to pentagon, then hexagon, then we have seen that your average coverage region will basically going to approximate that particular circular shape. So now next, when we are going to consider this hexagonal structure and when we are going to compare with the coverage region of this circular cell shape, then we can say that it is almost going to approximate the coverage area of your circular cell pattern. So it means on that particular basis, that is, we will going to have this non-overlapping region or lesser amount of void space, and apart from that we will going to have almost same number of base station installations. It will going to approximate the coverage of your circular cell shape. So hexagon structure will going to serve both these purposes. So that's why it would have been considered as your standard cell shape. Apart from that, this hexagonal structure is also having some special geometry which will going to help us in cellular computation. So how we will going to do that, we will going to discuss in our later slides. So for theoretical calculations, the hexagonal structure of cell is universally adopted. Some of the basic reasons are, although we have discussed, hexagon approximates the circle in terms of coverage area of omnidirectional antenna. This we have discussed, that this will going to approximately have the same area as your circular cell shape. Then with the use of this hexagonal geometry, fewer number of cells can cover the entire geographical region. So obviously if you are talking about this regular polygon hexagon, then while frequency planning, we will not going to have this non-overlapping region or void spaces if we are going to consider this hexagon cell structure for our cellular planning. So how does the actual cell shape look like? So suppose we have created our cellular system with this hexagonal structure, then it is actually will going to look like this particular structure. So this is completely irregular sort of structure which we actually going to obtain. And what is the reason behind that? That is, we have planned or deployed this sort of cell structure, but we are actually getting this. So there are lots of factors that are responsible for this irregular pattern. That is due to the heterogeneity exist in your physical environment. Whether we are talking about your urban area, suburban area, the geographical conditions are little bit different. If you are talking about your urban area, it is full of your buildings as well as other structures. Apart from that, if you are talking about your hilly area or your suburban areas, that is full of your plants as well as trees. So on those structures, our signal will going to get absorbed, or its actual coverage area will going to distorted in comparison to for which it has been deployed. So actual radio coverage area of cell is amorphous, that is irregular shaped, which is obtained by field measurement and by using prediction models through computer simulation. So this actual area coverage would have been called as the footprint. So this is how our actual cell shape will going to look like. So let us consider that this particular figure is basically showing the cellular planning over a certain geographical area, and these whatever this mentioned, these particular cells, they will basically are your co-channel cells. As of now, just consider that co-channel cells are the cells which will going to possess the same frequency ranges for their communication purpose. So if we considered about your coordinate axis, that is your x coordinate as well as this y coordinate. So in order to perform this cellular computation, we will going to define a new axis which will going to be made via adding the center point of various cells, and we may consider any particular direction. So as of now, we have considered this particular axis as your u axis, which is going to join the center point that are lying over the same line, that is this particular center, this particular center, this particular center, this particular center, this particular center. So we have made this particular line and we have called them as your u axis. And another axis we have formed while moving anti-clockwise 60-degree angle. Wherever we will going to move down, we have made this particular axis as your v axis. So this particular axis also we have formed via joining the central point of your hexagons. So we basically have formed two axes, that is your u axis and v axis, and we will try to compute our distance calculation in terms of these axes only. So as we have already mentioned that these cells, this cell and this cell, they will going to possess your same frequency ranges, or you could say they are your co-channel cells. So here our objective is just to find out this co-channel distance in terms of unit cell distances. So how we will going to do that? Let us discuss. So let us say here P is any point, and we have to evaluate this distances in terms of your original rectangular axis, that is your x and y. So if we closely observe that this is nothing but a rectangle, so that is why this distance and this distance are same, and similarly this distance and this distance, they are also same. So our objective is just we need to evaluate the value of this r in terms of x and y. So how are we going to do that? Let us understand it. So if this particular point is u, it means over u axis we have traveled u number of integers, and over this v axis we have traveled this v number of integer. So we will going to get over this particular point P. So how we will going to compute the coordinates of u and v in terms of this x and y. So if you closely observe that this particular right angle triangle, this is your u, and if we talk about this particular angle, since this complete angle is your 60 degree and this complete is your 90 degree, so 90 minus 60, it means this angle turns out to be your 30 degree. I'm talking about this angle. So this is your 30 degree angle, and if this is u, this is your 30 degree, then what about this distance? This distance is nothing but your u cos 30, and similarly what about this particular distance? This is nothing but your u sin 30. So if this is u sin 30, then this is also u sin 30, I mean up till this distance from this origin to this particular point. If we consider about this particular right angle triangle, here this is your x-axis and this is your y-axis, and this particular distance is your r, that is from origin to P, distance or radii is your r. So how we will going to evaluate this r in terms of your rectangular coordinate system, that is your x and y. So from the Pythagoras theorem, this r would have been given as your r square will be equal to this square plus this square. Fine. And what about this value v in terms of your xy coordinate axis? Up till this point, this is your u sin 30, and this particular portion is nothing but your v. So this complete variation will turns out to be your u sin 30 plus v, and this is nothing but your u cos 30. Both these two distances are known to you, that is your u cos 30 and u sin 30 plus v. So in order to evaluate this value r from Pythagoras theorem, we can write it as r square will be equal to u cos 30 whole square plus u sin 30 plus v whole square. So this is how we will going to evaluate this value of r. So hopefully axis transformation might get clear to you. And now since our objective is to evaluate this particular distance d in terms of unit cell radii distances, so we will going to look through another slides, that is how we will going to evaluate this cochannel distances. So then again, one important parameter about your hexagon cell structure is if you are going to join the vertices of any regular hexagon to its centers, we will going to get this 6 equilateral triangles. This is our hexagon cellular pattern, where we have mentioned this that this particular center to this particular center, the distance is d and your cellular radii is r. So if we are going to consider this d is equal to 1 unit, then how we will going to represent this cell radii r in terms of unit cell distances? This is showing nothing but your equilateral triangle whose all three sides are your r. Since this is r, and from the special geometry of hexagon, we know that when we will going to join this particular vertices to this center, this and this, so all three sides are same since it is your equilateral triangle. So all three sides are your equal to r, and we have considered that the distance between any two consecutive centers of your hexagon is being considered as your d. So this turns out to be your d by 2. So all three angles, that is this angle as well as this angle, all three angles are your 60 degree. And if we talk about this particular angle, so it is the property of your equilateral triangle that if you are going to drop a perpendicular from the vertices to the base of an equilateral triangle, it will going to divide into two parts, and this is also your angle bisector also. So this particular angle turns out to be your 30 degree. So if we talk about this particular right angle triangle, this angle is 30 degree, this is your r. So this side d by 2, that will be equal to your r cos 30. So it means d by 2 will be equal to r cos 30. So conversely we can say that d will be equal to r root 3. So now I just have summarized whatever we have discussed through our previous slides. So axis UV intersect at 60 degree. This is we had discussed. Then unit scale distance between cell centers, we have assumed that small value d will be equal to unity. Then if the cell radius to point of the hexagon is r, then 2r cos 30 will be equal to 1 or r is equal to 1 over root 3. Since we have considered d as your unit distance, so instead of this d we have put this 1, so r turns out to be 1 over root 3. So to find out the distance of point uv from the origin, use xy to uv coordinate transformations such as your r square will be equal to x square plus y square. Here this particular equation is showing that in order to reach to that particular point P on your xy coordinate system, we must have to move x number of units in your x-axis and y number of units to your y-axis, and that will going to show the position of that particular point P. So that r square will be equal to x square plus y square. So x is equal to u cos 30 degree. We have already seen that from that geometrical figure. And y is equal to v plus u sin 30 degree. This is also we have seen from our last figure only. So by putting the value of this x and y in this particular equation, what we are getting is r is equal to under root of u square plus uv plus v square. Since u square sin square 30 plus u square cos square 30, if we are going to take the common value u square, then you are left with this sin square 30 plus cos square 30, that is nothing but equal to 1. So this will going to gives us this particular relationship, that is r is equal to u square plus uv plus v square to the power 1 by 2 or square root of this particular stuff. So this is your important relationship. So now this particular discussion, whatever we have made so far, how we will going to locate the co-channel cells. So here criteria is quite simpler. With the help of this equation, to locate the co-channel cells, we start from any reference cell and move I cells along the u-axis, then j cells along the v-axis, and wherever we will going to now at this particular moment, that would have been considered as your co-channel cells. So I mean one more slide is there how to locate the particular co-channel cell, but as of now just consider that you are standing over certain reference cell, and in order to find out another co-channel cell, you must have to move any integer number of cells on your u-axis, then any integer number of cells on your v-axis. So wherever you will going to reach, that particular cell would have been considered as or called as your co-channel cell, and basically you will going to provide same frequency bands to that particular cell only for cellular planning. So hence the distance between co-channel cells among the adjacent cells would have been given as d will be equal to I square plus ij plus j square to the power 1 by 2 or under root of I square plus ij plus j square. So the co-channel distances would have been given by this particular, and please keep in mind here we are only being talking about the scaled distances, since we have made the distance between two consecutive cell centers is unity. So in that particular sake, this is showing nothing but your integer values. So in order to formulate or evaluate the actual cell distance, we must have to multiply with them with proper scaling factor, whereas this n is basically representing that how many number of cells will be there that will going to reside in the cluster. So that will be equal to I square plus ij plus j square. So this is basically giving us the value of total number of cells that will going to lie inside the cluster, and cluster we have already described that it is the combination of cells which will going to have different frequency bands. So the number of cells in the cluster n would have been given by this particular equation. So here I and j are the integers, whereas the possible values of n are yours 1, 3, 4, 7, 12 and 19. So please keep in mind that we cannot talk about any specific cluster where we will be having certain predetermined number of cells. That is, we cannot design any particular system whose cluster will going to have this 2 number of cells. It is not possible for this cellular planning. So the different number of cells that will going to reside in your cluster is your 1, 3, 4, 7, 12 and 19, which would have been governed by this particular equation, that is I square plus ij plus j square. So we just have to put different integer values of I and j and we're going to get these values, that is how many number of cells will be there inside the cluster. So this particular table is basically showing that how we will going to obtain the number of cells inside the cluster and the effective distances. So this is I and j, these are your integer values. This is your n, which will basically going to signify the number of cells in your reuse pattern, and this is basically showing your normalized distance, that is d is equal to root of n. So if we are going to take this value of I is equal to 1 and j is equal to 0, so n is equal to I square plus j square plus ij. So we just have put this value I and j and we are getting this n is equal to 1 and d is also equal to 1. So when we have put this I value 1 and j value 1, then in that particular case 1 square plus 1 square plus 1 into 1, that is turns out to be your 3, and the normalized distance will be equal to under root of n, that turns out to be 1.732. So this is how we have made this particular table. So now next is how to find the co-channel cell location. That is how you are going to find a particular co-channel cell location. So to find the co-channel neighbors of a cell, what we have to do is we just have to move I number of cells perpendicular to the hexagon boundary. Obviously here we are talking about we have to move I number of cells over your U axis. Then we have to turn 60 degree counterclockwise or anti-clockwise, which is nothing but your V axis, and we have to move j number of cells on that particular V axis, and to whichever cell we have now, then that particular cell would have been considered as your co-channel cell. So as this particular example is showing, I is equal to 2 and j is equal to 2. So how we will going to locate the co-channel cell? So suppose this is your reference cell. So in order to find out its co-channel cell, whose valuation would have been given as I is equal to 2 and j is equal to 2. So here we just have to move I number of cells in your U axis, that is from here to here 1 and this 2, and then again we have to move counterclockwise 60 degree angle. So this angle is nothing but your 60 degree. So we just have moved counterclockwise 60 degree and again move 2 number of cells, that is 1 and 2 over your V axis, and we are lying over at this particular cell. So this cell and this cell will going to be your co-channel cells, or in these two cells we will going to apply same frequencies for the communication or transmission. And for this particular sake, where I is equal to 2 and j is equal to 2, the number of cells in the cluster will be given as your n is equal to I square plus ij plus j square, that is your 2 square plus 2 square plus 2 into 2. So that turns out to be 12. So this is how we will going to locate the co-channel cell. Now next point is your reuse ratio. So what do you mean by that? So this ratio will basically going to gives us the information that how many number of times we may reuse your frequency pattern. So for hexagonal cell, the reuse distance is being given as d is equal to under root 3n times of r, and since this is your normalized distance, to just in order to find out the actual valuation, we must have to multiply it with this your radii. So where r is the cell size and n is the cluster size. So d turns out to be under root of 3 times of n. So reuse factor would have been defined as it is the ratio of your d by r, where d we had already defined, it would have been given as your under root 3n times of r, and where r is your cell radii. So this cell reuse ratio is denoted by this small value q, and it will be equal to d by r. So that turns out to be under root 3 of n, and this reuse factor will basically going to gives us the information that how many number of times we can further reuse our frequency bands in your cellular planning. So hopefully you guys have got the insight about special geometry of your hexagon. Apart from that, why hexagonal structure would have been chosen. In case of any doubt, you can ask me in the comment section. I'll try to solve them out as soon as possible. So these are the references. Thank you very much for your patient hearing.